And yeah, so the solution to unsupervised learning, just give it all to your Kolmogorov complexity, to your Kolmogorov compressor. Okay. And the final thing is, I'll mention that this kind of joint compression is maximum likelihood if you don't overfit. If you have a data set, then the sum of the likelihood given your parameters is the cost of compressing the data set. You also need the cost to pay the cost of compressing the parameters. But you can kind of see if you now want to compress two data sets, no problem. Just add more points to your training set, to your data set, and add the terms to the sum. So this concatenation, this joint compression is very natural in a machine learning context, which is why it was worth the hassle of saying, yeah, like we have our conditional Kolmogorov complexity, and then I made some argument, I made some claim without fully defending it, but it is possible to defend it. That using regular, just compress everything Kolmogorov complexity works also. And so I think this is elegant. I like it. Because then it says, well, okay, if you squint hard enough, you can say that this explains what our neural networks are doing. You can say, hey, SGD over big neural networks is our big program search. Bigger neural networks approximate the Kolmogorov compressor more and more and better and better. And so maybe this is also why we like big neural nets, because we approach the unapproachable idea of the Kolmogorov compressor, which truly has no regret, and we just want to have less and less regret as we train larger and larger. As we train larger and larger neural nets, as far as extracting predictive value is concerned. Now, the way this applies to the GPT models, I claim that it applies to the GPT models also, this theory. But the thing that's a little bit tricky with the GPT models is that the theory of their behavior can also be explained without making any references to compression or unsupervised learning. You just say, no, it's just the conditional distribution of text on the internet. Few-shot learning, just imagine a document with some repeated patterns. The pattern is probably going to continue. So the GPT models can intuitively be explained, at least their few-shot behavior can definitely be explained without alluding to this theory. And so I thought it would be nice. Can we find some other direct validation of this theory? Now, can we find a different domain, like vision? Because vision, you have pixels. Can you show that doing this on pixels will lead to good unsupervised learning? And the answer is yes, you can. This is work we've done in 2020, which is called the IGPT. And it's an expensive proof of concept. It was not meant to be a practical procedure. It meant to be a paper that showed that if you have really good next step predictor, you're going to do great unsupervised learning. And it was proved in the image domain. And there, I'll just spell it out. You have your image. You turn it into a sequence of pixels. Each pixel should be given some discrete value of intensity. And then just do next pixel prediction with the same transformer. That's it. Different from BERT. Just next token prediction, because this maximizes the likelihood, therefore compresses. And like we see, one immediate result we see, these are results on CIFAR 10. You have models of different sizes. This is their next step prediction accuracy on their pixel prediction task, on their unsupervised learning task. And this is linear probe accuracy. Linear probe, when you pick some layer inside your neural net, the best layer, fit a linear classifier and see how well it does. You got these nice looking curves and they start to get more and more similar. It's kind of what you want. It's like, it's working. Pixel prediction of the same variety as next word prediction. Not just pixel, not mere pixel prediction, but next pixel prediction. Leads to better. Leads to better and better unsupervised learning. I thought that was pretty cool. And we tried it, we scaled it up to various degrees, and we showed that indeed it learns reasonably well, where we came close, but we didn't like fully match the gap between our unsupervised learning and the best unsupervised learning of the day on ImageNet. But it was clearly it did feel like it scaled, and it was a matter of compute. Because these things use large, high-resolution images, and we use like tiny 64 by 64 images with giant transformers for the day, tiny by today's standards, but giant for the day, 6 billion parameters. So this is like, yeah, you do your unsupervised next pixel prediction on a big image data set, and then you fit your linear probe on ImageNet, and you get strong results. Like, okay, that is cool. CFAR, yeah, like we got one of the cool things. If we got 99% on CFAR 10 with this, that was cool. That 2020 was a different time, but it was cool. I'll close with a couple of comments on linear representations. The thing, look, I like the compression theory because I feel like it just bothered me for a long time that you couldn't think rigorously about unsupervised learning. I claim now you can, at least to some partial degree. Still lots of waving of hands is needed, but maybe a bit less than before. But it doesn't say why your representations should be linearly separable. It doesn't say why linear probes should happen. But linear representations happen all the time, and the reason for their formation must be deep and profound, and I think we might be able to crisply articulate it at some point. One thing which I thought was interesting is that these next pixel prediction models, autoaggressive models, seem to have better linear representations than BERT. And like the blue accuracy is BERT versus autoaggressive. I'm not sure why that is. Or rather, I can speculate, have some speculations, but it would be nice to, I think it would be nice to gain more understanding for why, like really why those linear representations are formed. And yeah, this is the end. Thank you for your attention.
Could you provide the speculation?
Yeah, oh yeah. I think the speculation is basically that if you're doing next pixel prediction, you're predicting the next pixel from all the previous pixels. So you need to look at the long-range structure. But in BERT, you have your vector, and let's say you drop 25% of the tokens, of the pixels in this case. Then any prediction that you have can actually be done quite well by looking a little bit into the past and a little bit into the future. So you remove all the hard prediction tasks, or you make them much easier. The hardest prediction task in the next pixel prediction is a lot harder than the hardest prediction task in the BERT prediction case. So this is an argument. We maybe even be able to test it if we think a little, if we try to design an experiment to test it. But yeah, that's a speculation.
Is there a more robust 2D version of next pixel prediction?
I would say more robust. I would say anything you do at all that turns a neural network into a probabilistic model that assigns probabilities to different inputs is that. So the other big way of doing next token prediction is diffusion models. Diffusion models also, like not the ones that are, so the diffusion models that people use in like high quality image generators don't really maximize the likelihood of their inputs. They have a different objective, but the most original formulation is maximizing likelihood. And by the way, the diffusion model is a counter argument the diffusion model also, I would claim, should have worse representations than a next token prediction model for the same reason that BERT doesn't. So this further, in my mind, increases the mystery of what leads to linear representations to form.
Yeah, thanks for the talk. I like the analogy between Kolmogorov complexity and neural networks. I guess one kind of place where it seems like there's a disanalogy is that neural networks have training dynamics, and if you do something like just take all the computer programs, it's more memoryless, right? So if we're compressing with Kolmogorov complexity, like the order of the data doesn't matter. It clearly does for neural nets. You have like simple heuristics and features that are learned early in training that probably stick around late in training. And so I guess you have thoughts on how to think about that in the context of this picture.
Yeah, I mean, The analogy isn't perfect, that is true, and the way in which you describe it's imperfect. Like, the place where the analogy breaks down the most is in the search procedure, right? This is really what you're alluding to, like, hey, like order of data matters. Why? Because we are using a weak search procedure. Kolmogorov compressor uses the infinitely expensive search procedure of just enumerate everything from scratch each time. So yeah, I mean, it is, I mean, I would say that caution should be used with this particular analogy. It's very clearly not universally applicable, but I do think that I do think that there is some value here in explaining where unsupervised learning comes from.
So your formal going back and forth between compression and next bit prediction, you're connecting that to relating unsupervised learning to supervised learning. So if you sort of backtrack from cryptography, there's sort of a theory goes back to the 80s where they talk about compression being equivalent to next bit prediction, being equivalent to being able to distinguish between distribution. So if you have an algorithm that can distinguish, then you have an algorithm that can predict, then you have an algorithm that can compress. I mean, cryptography is the other way, right? You say there is no way to compress, therefore there is no way to distinguish, and therefore there is no way to distinguish. So I wonder if this idea of being able to distinguish, how could that would that translate to anything natural?
So I think I understand. I think I understand the question. Let me paraphrase. So I'm not super well versed in the area that you mentioned, but you're saying if you can distinguish to distribution, you can use that distinguishability to make to predict. And I guess the question would be, what's the I have some.
You have samples from one, you have samples from the other, and you can tell them apart. So
and so I guess my question is, how well can you predict? Well, you're talking about you can predict a little bit. Is that what you're referring to?
50+ steps. So you can predict what the next bit would be, let's say, in a sample.
So yeah.
What you can predict.
I mean, I can mention one thing that is related, which is energy-based models. So energy-based models offer yet another way of turning neural networks into probability distributions, where an energy-based model will say, I just give me your configuration of vectors, and I'm just going to tell you how it feels, and then you normalize over all of them. And I feel like when it comes to energy-based models, in particular, ratios of distributions correspond to differences of energy. Maybe there is some relation to what you're saying. I think I'm probably not like precisely commenting on the thing which you said, but I don't think I have anything more to add, unfortunately.
Ilya, maybe I'll just put in a tiny word to defend the honor of VC dimension.
Go ahead.
Well, so, I mean, in 2007, I had this theorem about pack learning of quantum states, right? And this was precisely an example where even if you don't care about infinite precision, even if you discretize the state space, like you look at the VC dimension or the fat chattering dimension or whatever, and it is exponentially smaller than the log of the size of the hypothesis class. So I do think there are cases where you still want VC dimension.
That is a cool example.
So I didn't completely follow your notation. Capital X was a sample from a distribution.
No.
The distribution is
The data set.
So then the transformer SGD, I'm not sure if you can think of it as the best program for compressing the distribution. Maybe because it's only given one sample at a time.
That's true. There is one other assumption that we are making. So if you look at the total training loss, say you have some neural network, doesn't need to be a transformer, some neural network which assigns log probabilities to your data. And you have some large number of training cases. You can run the neural network, and you have some neural network. You can compute its log probability on each case, and you can take their sum. And that's going to be the log probability that the neural network assigns to the entire data set. Now, the neural network is this particular formulation makes the neural network unable to explicitly notice, like maybe temporal or any kind of structure in the order of the data. But I still claim it's meaningful to say that, yeah, like, okay, you can compute the entire log probability of the data set, and that gives you your negative log probability, literally the number of bits you need to compress this data set relative to using this neural network as a compressor.
Yeah, if I could paraphrase, I think you're arguing for compression as a framework for understanding or motivating unsupervised learning. And a point you made at the end was that if you apply that framework to language models, to next word prediction, it can feel a little maybe superficial because next word prediction, any text task can be converted to next word prediction. And so unsupervised learning is kind of superficially the same as supervised learning for text. So then we turn to image GPT, where you can't formulate any image task as next pixel prediction. Maybe you could, but let's just say you can't. But then you can use the linear representation as a way of showing that compression is a good way to formulate unsupervised learning. But then there are highly effective compressors that wouldn't give you a useful linear representation. So I'm wondering, are there any cases where unsupervised learning and supervised learning are not superficially the same, like in text, but that you don't require your compressor to give you an effective linear representation to show that compression is a good unsupervised objective?
Yes. So that's a very I have thoughts on this question. So first of all, I will say that the linear representation, a good linear representation, is a bonus. At no point does this argument say, and therefore linear representations should emerge. However, I would argue that the theory does say that good fine-tuning should emerge, because joint compression is kind of like hacky approximate fine-tuning using the bad search algorithm, which is SGD. Now we know that the evidence from these old experiments suggests that BERT learns worse linear representations than next pixel prediction when run on images. And perhaps the same is true for diffusion models. That seems highly likely. I think it'll be very interesting to see how the fine-tuning of diffusion models compare. Maybe someone knows already here.
I wonder if you can take your ideas for unsupervised learning and bring them back. It seems to me that there could be some insights you could take back to supervised learning, which back learning doesn't cover.
Well, I think here this gives you more like insight into the particular insight you might get here is insight into the function class, the desired function class. Like you want your neural net to have many layers, for example, right? If you have many layers, it can do more thinking. You want those layers to be wider, bigger, bigger neural nets. I mean, essentially, this is like what the field has already discovered.
But you might not need more examples than number of parameters. In supervised learning, this might give you an explanation for why you don't need necessarily more parameters.
Like that's right. So this might, for example, be like the weakness of this theory, by the way, this theory has a huge practical weakness, which is it ignores compute cost. It only focuses on information. So like you're all familiar with the universal transformer. Maybe it's like basically it's a transformer. We use the same weights at each layer. It's a great idea, except that if you want to have a lot of parameters, you need to pay for it a lot with compute. Nobody wants to do that. You don't ignore compute cost. This ignores compute cost. If you ignore compute cost, it gives you a recipe of how to proceed.
What do you think the importance is of the autoregressive modeling in particular of the probability distribution? Like you can view BERT as sort of kind of doing maximum likelihood training, right? I think you can find ways to sample out with BERT, for example.
So certainly diffusion models can be set up to be maximum likelihood models. And so All this theory predicts that diffusion models should also be, it should be possible to make diffusion models to do equally great things, perhaps with some constant factors of, because this, this is like, as the earlier answer, this is not a compute sensitive theory. So it's going to say, okay, like maybe you need like a factor of 10 or 15 compute, and then things will be the same between the autoaggressive and diffusion model. The autoaggressive model has, it's just simple, it's convenient. Maybe the energy-based model will do even greater things, but from that perspective, they're all the same.
It seems like GPT-4 may be the best compressor at the moment, which presumably is the largest model out there as well. So on one hand, it's able to compress better. On the other hand, the size of the compressor itself is increasing. Or is it that it's actually not necessarily the case from the perspective of the theory or complexity?
Well, I mean, what matters is that the cost of the, like, what you really want is for the, like, there is another place in the way in which this theory doesn't quite correspond to reality, because this theory says, okay, you have a fixed data set, you want to compress it. But in the way we train the GPT models, you say, okay, you have this big training set, and then you have like a test set, which is assumed to be infinite. If the test set is infinite and you care about compressing the test set, then you don't care about the size of your compressor, so long as this test set size is much larger. So I would say that this is also like I would say, a disanalogy where some more careful thinking would be useful to get clarity.
Is it enough to use a validation set that's independent as long as it's separate? That kind of closes the gap.
Is it enough? It's a good thing. It's a good thing to do. Is it truly, like, the thing is, I think it's also, well, actually, like in the single epoch case, right? If you are in the single epoch case, then you can just, like, compute your log probes as you train, and that will be something like the model's compression of the data set. And that gives you also a good estimate of the validation set. So in the single epoch case, I think things are quite similar.
Just wanted to make you aware that there was a paper last month in findings of SEM. They have used GZ followed by a k-nearest neighbor classifier for just text classification. So no training, no parameter, just GZ compress strings, just like you should concatenate two strings together, compressor, compress them individually, and then compute distance. So they're in a way using the output of GZ as the full compressor.
Yeah. My only comment on that is that gzip is not a very strong compressor of text. So I think like it does show that things are possible to some degree, but like all the really meaty stuff happens when you like squeeze the last bits, if you see what I mean.
It seems like it works like a toy proof of concept, but it does work.
I think there was some bug there before this, so.
No, it doesn't work.
But that's resolved for now.
Since Jacob brought up curriculum effects and how they appear for neural nets, but not for you don't see it, but Kolmogorov complexity. We were just talking at lunch about like what is the current empirical situation about like how much do curriculum effects actually matter, and none of us knew the answer.
Well, it's like so it's a bit. I have a take on this, which is the easier. So we've done a lot of work as a field to make the transformer, like the architectures that we are using, to be relatively easy to optimize. We found good initializations, we found good hyperparameters. We made changes to the architecture so that training is as easy as possible. The easier is, the more easy the training optimization problem is, the less susceptible you are to curriculum effects. And like it's known, like for example, people who were training all kinds of exotic architectures, like neural Turing machines, for example, which are like these really complicated things. And it's super huge numbers of heterogeneous layers which are different. And that's when you need to be very, very careful with your curriculum. Because if you give it the full data set right away, it'll just fail.